Welcome to the new video of Explaino Tech. In this video I take you through the architecture of electric vehicle with the details of components involved in the operations during discharging and charging phase. To understand an electric vehicle, EV, it helps to view it as a high-powered ecosystem where energy is converted, managed, and distributed with incredible precision. And to execute this, the core components involved are explained in details here. 1. Battery pack. The high-voltage, HV, battery is the fuel tank of the EV. Unlike a laptop battery, it consists of hundreds or thousands of individual lithium-ion cells organized into modules. It typically operates at voltages ranging from 400 volts to 800 V. It stores energy in DC, direct current, form and is the heaviest and most expensive component of the vehicle. 2. Battery Management System, BMS. The BMS is the brain of the battery. It ensures the pack operates safely and efficiently by multiple features such as cell balancing, protection, state estimation such as state of charge, SOC, how much fuel is left, and state of health, SOH, the battery's remaining lifespan, and also communicating the limits to VCU as well as charging unit. 3. Electric motor. The motor converts electrical energy into mechanical energy to turn the wheels. Most modern EVs use permanent magnet synchronous motors, PMSM, or induction motors. During braking, the motor acts as a generator, converting kinetic energy back into electricity to recharge the battery, a process known as regenerative braking. 4. Inverter. The inverter is a critical middleman. The battery provides DC power, but most EV motors require AC, alternating current, to run. During drive, it converts DC from the battery to three-phase AC for the motor. Speed control. By varying the frequency of the AC signal, the inverter controls how fast the motor spins. 5. Transmission, reduction gear. EVs don't need multi-speed gearboxes, like a 6-speed manual, because electric motors provide high torque from 0 RPM and also rotates at high speed. Instead, they use a single-speed reduction gear. This reduces the high RPM of the motor to a lower, usable RPM for the wheels while multiplying torque. 6. Onboard charger, OBC. When you plug your car into a standard AC wall outlet or a level 2 home charger, the OBC takes over. It converts the AC electricity from the grid into the DC electricity required to charge the high-voltage battery. Note: fast DC chargers bypass the OBC and feed power directly to the battery. 7. DC-DC converter. While the motor runs on high voltage, 400 volts plus, the car's lights, wipers, infotainment, and sensors run on low voltage, 12 V. The DC-DC converter steps down the high voltage from the main battery pack to a lower level to power these components and keep the LV battery charged. 8. Charge plug. This is the physical interface where the external charging cable connects to the vehicle. Depending on the region and the car, these follow specific standards like CCS, Combined Charging System, CHAdeMO, or NACS, Tesla. It includes pins for power transfer and communication pins that allow the car and the charger to talk to each other. 9. Thermal management system. Batteries and power electronics perform best within a specific temperature range, usually 20 degrees Celsius to 40 degrees Celsius, and around 70 degrees Celsius for the motor. This system uses a combination of coolant loops, radiators, and sometimes a refrigerant-based chiller to cool the battery and motor during high-speed driving or fast charging. 10. LV battery, low voltage. Even an EV has a standard 12 volts lead-acid or lithium battery. It is essential for safety. It powers the vehicle's always-on systems such as different control units, manages the contactors, switches, that engage the high-voltage battery, and ensures the hazard lights and door locks work even if the main HV system is shut down. 11. Vehicle Control Unit, VCU. The VCU is the master controller of the entire car. It acts as the supervisor for all other subsystems. It processes the driver's inputs, accelerator pedal, brake, gear selector, and decides exactly how much torque the motor should produce, how much energy to regenerate, and manages the coordination between the BMS, inverter, and thermal systems. In the discharge phase, specifically the drive phase, shown in video, the electric vehicle is converting stored chemical energy into kinetic energy to move the vehicle. Think of this as the active state where the battery is powering the wheels. Here is the step-by-step breakdown of how that energy flows through the architecture. The process begins at the high voltage, HV, battery pack. The stored direct current, DC, energy exits the battery through high voltage cables, indicated by the glowing orange lines in your diagram. The battery management system, BMS, is constantly monitoring the discharge rate to ensure the cells don't overheat or drop below a safe voltage level. The DC electricity from battery travels to the inverter. This is a crucial step because the electric motor usually requires alternating current, AC, to operate efficiently. The inverter converts DC from the battery into three-phase AC. Based on how far you press the accelerator, the inverter adjusts the frequency and amplitude of the AC signal to control the motor's speed and torque. The AC power enters the electric motor, labeled as a 120 kilowatts PMSM in the video. The electrical energy creates a rotating magnetic field, which spins the motor's rotor. This is where electricity officially becomes mechanical motion. Because electric motors can spin at very high speeds, often up to 15,000 plus RPM, that speed needs to be reduced before it hits the wheels. The reduction gear, single-speed transmission, takes that high-speed rotation and reduces the RPM to a level suitable for driving. Significantly increases the torque sent to the axles to help the car accelerate quickly. Also, please make a note that even during the drive phase, a small amount of energy is being diverted through the DC-DC converter to power auxiliary systems like your headlights, dashboard, and sensors, ensuring the 12 volts LV battery stays topped up while you drive. In the charging phase shown in the video, the vehicle is stationary and pulling energy from the external grid to replenish the high voltage, HV, battery. This process is essentially the reverse of the discharge phase, but it involves specific conversion hardware to ensure the grid power is compatible with the battery. Here is the step-by-step breakdown of the energy flow. Power enters the vehicle through the charge plug. In this specific video, the green line represents AC, alternating current, coming from a home wall box or a public level 2 charger. Since the battery stores energy as DC, direct current, the AC power from the grid cannot be fed into it directly. The OBC acts as a gateway, converting the incoming AC into the DC required by the battery. It also regulates the voltage and current to match the battery's specific needs at that moment, ensuring the charging process is stable. During charging, the battery management system, BMS, is the most active component. It communicates with the external charger to request a specific amount of power. It checks the temperature of every cell. If the battery gets too warm, the BMS will signal the charger to slow down, derate the charging speed. BMS also ensures that no single cell is overcharged, which is critical for the long-term health and safety of the pack. The regulated DC power flows into the battery pack, HV. As the chemical reaction inside the lithium-ion cells stores the incoming energy, the state of charge, SOC, percentage increases. In the charging plus auxiliary discharge phase, the vehicle is performing a balancing act. It is pulling energy from the grid to fill the battery while simultaneously drawing energy from the battery, or directly from the charger, to run high-voltage cabin systems. This is a common scenario, such as when you are sitting in your car at a charging station with the air conditioning, HVAC, or heater running. While the battery is being charged, the auxiliary power distribution module, PDU, serves as the dispatch center for high-voltage power. Unlike a traditional car where the AC compressor is driven by a belt on the engine, an EV uses an electric HVAC compressor. This unit runs on high-voltage DC power, typically 400 volts. If you are heating the cabin or battery, the positive temperature coefficient, PTC, heater draws high-voltage power to generate heat electrically. This covers the essence of electric vehicle architecture. Thanks for watching. Hope you liked the video. Please share the video to your loved ones. Please like the video and subscribe the channel.